Okay, I am just continuing my last lecture on iron making and steel making in India. Okay, I have just discussed about the global steel production scenario vis-a-vis Indian steel production and in consumption pattern in the world as well as in India, and what was the major problems in steel making in India and what are the potential of steel making in India. We have already discussed, and in this lecture we will discuss about some alternative routes of iron making in India, and because how these alternative routes in India is important for Indian steel production point of view. And also we will talk about the that is education and research iron and steel in India. Okay, so alternative routes of iron making in India. So you can see that, as I said, that is coking coal is a major problem in India because we are dependent on coking coal, and we may develop food and we can buy coke from other countries also. We can bring some types of different types of coal, and then we can continue with the BF route that is required immediately. Basically, we cannot overnight convert to the DR and the SR process where we can use the non-coking coal. So we have to continue with the BF process. We have to import the coal, but we can increase the port and we can buy coal from other countries also. But at the same time, at the similar space, we have to develop our alternative routes of iron making in India. And India is proceeding in that direction too, to utilize the non-coking coal effectively. Okay, so that's why in that direction some steps has been taken that I am discussing. So we have seen that we have a great advantage over many other countries, including China also. We have a good reserves of iron ore still for next 50 years in terms of rich iron ore for the next 50 years. But India is crippled with limited and poor quality of coking coal. That's why that is there. That's why this coking coal, non-coking coal utilization, that we have a good reserve. We have to think about that thing parallel with the BF route. We have to think about development of the direct reduction. So this prompted India to explore alternative routes of iron making using non-coking coal and the natural gas. Natural gas, we have rather very limited resources, so we have to depend morely on the non-coking coal. Largely available non-coking coal and offshore gas along with the rich ore, which has prompted several direct reduction and smelting reduction routes successfully in India. You can know that is the several units has come. And most importantly, this has helped to disperse the Indian steel production from eastern India. Basically, we see initial development of the steel plant, all the steel plants were in the eastern India. Okay. And now eastern India, because in the eastern India's Chotanagpur plateau, that is very rich in the iron ore, coking coal, limestone, everything is there. That's why all the previous SAIL steel plant was grown there. Even TISCO, private party, there is a Tata Iron and Steel Company, that is also in the Jharkhand, that is also in the eastern region, because they can easily mine the iron ore and the coal as well as limestone. So that's why it was developed eastern India. But today, basically these are slowly dispersed from eastern India, because no more we are dependent, because we can use the natural gas, and that is available in the offshore, okay, near the western part of India. So the steel plant are also moving, because they are producing the DRI using the natural gas. So they are moving from eastern India. So dependent on the not only the rich iron ore. So iron ores are separate, other places are also available. So that is the thing. That is, this also helps. This is the alternative routes. When making the alternative routes using the non-coking coal as well as your gas-based process. So processes, that is the steel plant, are moving away from the eastern region. It is better basically. The steel plant should be uniformly distributed over India rather than in a segregated place. So this is also helped disperse Indian steel production from eastern India because of proximity of both coking coal and iron ore. That's why initially there. So then we have lot of space for the steel plant to grow. not in a particular place. Now, different places we can have lot of space for steel plant to grow. Deer that entered in 1981 has grown at a very faster rate. Today, more than 180 deer units are there, even more than that, right? Now, today is the leading producer of DRI, and it is producing more DRI compared to the gas-rich countries like Venezuela, Mexico, where DRI is mostly produced by gas-based process like Midrex and HOL process. So, this process are there, but today India is producing, because in India DRI production, lot of coal-based DRI production is there in that. That's why that India is producing the DRI both using the gas as well as coal, and coal share is more. That's why India DRI production is much higher. It is the leading producer today with 28 to 30 million tons per annum. That is the thing. So, some of the DR and SR units in India, you see during 1985 to 95, three major, that is the gas-based DR units were established in Esar, Hazira, Gujarat. Presently, there is ArcelorMittal, this company, and then 3.6 million ton Ispat industry Mumbai Mittal. That is the 3.6 in the Ispat industry, 3.6 million ton, 1.6 million ton. And Bikram Ispat, that now Welspun Maxsteel Goenka is around 0.9 million ton. So, these are basically the major DR units, and obviously that is the JSW also has okay. JSW has also, in the Dolvi also we have now, that is the DRI plants, okay, their Midrex based DRI plant is there. That is the Midrex DRI plant, Dolvi also Midrex DRI plant, and that uses the coke oven gas as well as the coke oven as well as the natural gas, they mix up, because natural gas, you know, there is a less amount is there, and coke oven gas contain lots of hydrogen. So, Dolvi plant operate with the 2:1 coke oven to natural gas. So, that is also there. Domestic DRI capacity is increased by around 280% in 8 years from 2005 to 13. So, DRI capacity has increased significantly to it around 3 times from 2005 to 13. Esar now today is the largest single location of gas-based. Esar is the single largest location of the gas-based DRI HBI plant of the world. 3.6 million ton is produced by the Esar. Now, Esar is now taken up by the ArcelorMittal. So, anyway, so Esar is the largest single location of gas-based DRI production. Similarly, JSPL is the single largest location of coal-based DRI plant in the world. 1.32 million ton coal-based DRI and 2.2 million ton syngas-based DRI. And as I said, that is the Raigarh in Raipur. They have 1.32 million ton of coal-based rotary kiln furnace-based coal-based DRI production unit. Also, they have 2 million ton DRI unit, that is the basically coal-based syngas and Midrex. They have retrofitted the Midrex with the coal-based syngas, and that is in their Angul plant in Odisha, and that produces around 2 million ton of DRI. And so, thus combining these two, the JSPL is the largest single location for coal-based DRI in the world. After 1994, no natural gas-based DRI HBI plant has been set up, and it is mostly now the stress on the coal-based, because coal plenty we have. Major growth in the coal-based sector from 2003 to 4 and 8 to 9. Presently, no small coal-based plants, and the coal-based DRI rotary kiln furnace, that uses the rotary kiln, that pollutes the atmosphere significantly, and they don't follow the norms or environmental norms. That's why the small scale coal-based plants are not allowed by the state government, because the pollution control board, they don't allow it because they don't follow these norms. Because initially the Raniganj area in the West Bengal, a lot of these small DRI plants came up, coal-based rotary kiln furnace-based DRI plant came, and then they were mushrooming it, but they are not looking after the environment, which is not a sustainable process, and then it is under the scrutiny of the state government, and no small scale coal based plants are allowed. 50 tons, 100 tons per day, those things are not allowed. Total DRI production in India today 30 million ton, leading producer in the world, and shortage of NG are being replaced by the coke oven gas. Coke oven gas is a very good gas because it contains a lot of hydrogen and it can be effectively used for DRI reduction. Corex gas, JSW is using the Corex gas to run their DRI plant, and the coal based syngas, now JSPL is pioneered in this direction. They have used the Lurgi technology to produce the coal based syngas, and that syngas is fed into the Midrex unit to produce the DRI. So, 2 Corex SR units of each capacity 2000 million ton per day, that is the 2000 tons per day, okay, 0.8 million ton per annum each. Okay, there is a 2 Corex unit at JSW Bellary, Karnataka, and 2 similar unit at SR Hazira, Gujarat exist today. So, Corex plant, as I said, 2 Corex plants of each capacity of 2000 tons per day. Okay, 2 plants are there in JSW Dolby and 2 are there in JSW Bellary and 2 are there in what is that, SR Hazira. Okay, these Corex plants are there. So, so this is the status of DRI plants in India, and India has a very potential to develop in this area further. Basically, so far in India, technology do not exist that can use the waste, iron bearing waste. So, the bright future ahead of some technology that can utilize this iron bearing waste material, and RHF can be one of the very good technology, because in the RHF you can convert it to the sponge and then you can melt it. And another technology may be the smelting reduction. There is a Hismel process type of process, has a very bright future in India. Some of the comparative data of Indian iron and steel sector versus global benchmark. If you see the productivity wise, and blast furnace productivity transferred in terms of tons per day per meter cube, India is 1.5 to 2.5 compared to global benchmark of 2.5 to 3.5. So, Indian production is quite less, we can improve it, and also sometimes we run under production also. Whatever the capacity, we cannot produce that much because of lack of demand or some other issues that are involved into the plants. So, most of the time our plant goes with under capacity, run with the under capacity. Okay, so that is on the another major problem. Also, along with that, productivity is quite low compared to the global benchmark. Energy consumption, gigacalorie per ton of crude steel, if you see, that is the India is 6 to 6.5 compared to the global benchmark of 4.5 to 5.5. In terms of kilojoule, it is around 25, that is the, in India is around 28 gigajoule per ton of crude steel, compared to it is around is much less, around say 22 gigajoule per ton of hot metal. Coke rate kg per ton of hot metal in India is around 350 to 500 kg of coke per ton of hot metal, and global benchmark is 300 to 350. PCI kg per ton of hot metal, India 50 to 200. Some plants are there very modernized, they are 200, but mostly it is very less. It is 50 and 100 around. So, 50 to 200, and global benchmark is around 150 to 250. So, SMS slag, that is the steel melting slag kg per ton of crude steel, 180 to 200 kg per ton of crude steel, and global benchmark is less than 100 kg SNS slag. CO2 emission ton per crude steel, that is a ton per ton of crude steel, in India is 2.8 to 3, is very high compared to global benchmark of 1.7 to 1.9, and India is desperately trying to reduce this emission okay, to maintain the that is protocol, environmental protocol. They have to reduce it to 2.2, basically ton per ton of crude steel production. So now I will talk about something about the education and research in India, because as I said, now India need some cutting edge technology, of indigenous cutting edge technology, and very energy efficient technology is required. And for that, I think in India, research and education has to be revamped for day-to-day innovation and for futuristic innovation of technologies. So, but you can see still we are countries gearing for 200 million ton of steel in the near future. The steel education and research has taken the backseat. This is very unfortunate. There is a decline in steel market in 1990, and the migration of graduating engineers to IT sector and management jobs has inflicted irreversible damage, resulting in acute shortage of qualified engineers in plant and the R&D sector. That is the thing. Basically, most of the graduating engineers shifted to IT sector and management job in not only metallurgy, all departments. So, reluctance of the bright student adopting for iron and steel as a viable career option has largely affected the academia. Today, we do not have that gamut of academician that used to exist in the 1980s, because we have not a very bright student that adopting for iron and steel as a viable career, both for the industry as well as for the academics. So, they are not going in that iron and steel. So, there is a reluctance. And reluctance of the bright student in iron and steel sector. Possibly the job is not very lucrative, or job is not a white collar job, money is not much, or development scope is not much. Whatever it may be, there is a huge reluctance of the adopting iron and steel career. As a result, academia is also suffering. Academia is also not getting good student, okay, for research and education, research and development. As a result, there is the faculty is also shrinking significantly, because no good student, no good faculty in the future. That's why that is the thing I just talked about, and it has significantly decreased and subsequently affected the postgraduate teaching and research program in many departments, and it has formed a vicious circle of lower and lower iron and steel research in India, because no bright student, no faculty, no bright student. As a result, the research in the area of iron and steel is shrinking day by day. Some initiative has been taken by Ministry of Steel, like steel chair professor they have introduced, and also they have given some intense incentives to the third year and fourth year students, some scholarship such that they adopt career for iron and steel, but it doesn't look to be very effective. But country seems to lack a critical manpower today, because iron and steel research is very few in India. We can hand count what the person who are doing the iron and steel research. And when I visited international conference in Japan and China, then you can find so number of people are working in different areas of iron and steel. I have seen some 50 researchers are there in the coal making also, in the coke making, coke beneficiation. So there, but India you can hand count who are the people who are doing the iron and steel research today. So we are very much lacking. If you say lack critical manpower, it will be less. We are very much critical. We are just, it is a critical, we do not have any critical mass to do the iron and steel research in India today. So if we see how the metallurgy program evolved with time, the first metallurgy program in the country was established in, that is the Banaras Hindu University in 1923, and subsequently to the BA College, Shibpur in West Bengal in 1939. During 1960 and 70, various IITs and NITs introduced undergraduate program in metallurgy. However, between 70 and 2010, only 6 other colleges added metallurgy. So you can understand there is a declining in the metallurgy interest. The first PhD from BHU in 1955 and regular PhDs from 1960 from other departments of other institute. Then it started. From 1990, many metallurgy departments changed its name from the Department of Metallurgical and Materials Engineering. So metallurgy department has been named Department of Metallurgical and Materials Engineering, and materials attachment has become more, and tuned the research more towards emerging materials and de-emphasizing the traditional materials like metals like iron. Traditional subjects like extractive metallurgy, fuel mineral engineering are cut short to make places for the course related to the materials like electronic materials, nanomaterials, biomaterials. They are giving more weightage. So subsequently, as a result, new engineering graduate remains underexposed to metal processing and allied subject. They remain really underexposed. So how the interest will grow? So several industrial R&D have also been established, but innovative and path-breaking technology is yet to emerge. From where this technology will come? That requires a good manpower. There is a good research team. So that will be industry, R&D, and the academia and industry. That should be a good team, and not only a couple of people. There should be large number of people working together, such that we can have some innovative and path-breaking technology. So what is required is the high quality manpower. That is very much required, and unless students are interested, you cannot do that. So we have to bring back the students to the curriculum, and we have to open up the more course on the extractive metallurgy, such that the student get exposed to grow interest and high quality manpower development. And also the steel plant also has some role to play, such that they can make a very good place for the bright student to stay there. So high quality manpower and world class infrastructure. There is the infrastructure we are also lacking. There is the, especially in the iron and steel research, since very limited number of faculty and the funding is very limited, the world class infrastructure we are lacking. We do not have world class infrastructure. And then creative environment and bright mind, creative environment are prerequisite for novel R&D outputs. So with this, I will come to the conclusion of this section. That is, in 2018, India became the second largest producer of steel with 106 million ton per annum. And major steel making companies in India today are JSW Steel, JSPL, Tata Steel, SAIL and RINL. Large domestic market and availability of rich iron ore for next 50 years indicate a bright future for India in the steel making. That is the bright future. We have bottlenecks also. Bottleneck is the coal. Okay, we do not have good coking coal, so we have to depend on the since we cannot overnight change to other alternative technologies, we have to run with the BFBF process to expand into the iron and steel, and we have to import the coking coal abroad, but we can increase the number of ports such that we can tap the source from other parts of the world also. And and also thing is that, and also we have to have increase the some bottlenecks are there with respect to the labor productivity, management and the infrastructure, and all this we have to look into and we have to improve it. And India now today has diverted attention. It is very likely and it is very a good step to move towards the alternative routes of iron making, also utilizing non-coking coal and the gas whatever available, or based on the syngas we have to produce synthetic gas on that thing, or you can utilize the process gas to produce the DRI. Whatever way we have to go for the alternative routes of iron making parallelly with the BFBF process. India is the global leader of DRI production, 330 million ton, but it is not enough. We have to increase this production to a significant way, such that we can increase the DRI scrap, hot metal and EF production. That is the DRI EF route we can increase significantly over the BFBF route. Okay, so that our target should be is the DRI EF route. It should increase progressively, exponentially, and the BFBF route we cannot sustain for a long time because of the coking coal. The number of professionals working in the iron and steel research and education has diminished significantly today. And this is a vicious circle basically. And our course curriculum is changing. We are not getting bright students. Students are not getting more exposed to the more of extractive metallurgy course. We are not getting good bright student. As a result, faculty is not generating. And as a result, iron and steel research in India is depleting day by day. So this thing also we have to keep in mind, and we have to give more importance on the academia also. And we have to develop world-class infrastructure in the iron and steel research, and we have to have a very bright manpower, innovative manpower, such that in the future we can come up with the very novel technology, energy efficient technology that can produce steel at a much cheaper rate, and very good quality steel at a cheaper rate we can produce. Okay, so with these words I will conclude my lecture here. Thank you very much.